Fundamental theorem of arithmetic. Definition: every composite number can be uniquely expressed as a product of primes for the order in which these prime factors occur. For the definition, we must have the knowledge for the composite number, for the primes, and what is the meaning of uniquely expressed, and what is the order it is talking here. We will talk about these 4 points here so we can fully clear out this concept and understand it very well. So the definition of prime number, as you already know, is just a quick reason. Whole numbers which have only two factors, 1 and the number itself. Example: 5 is a prime number, as the factors of 5 are the number itself and 1. So this is a prime number, composite number. Whole numbers which have at least one factor other than 1 and the number itself are composite numbers. Example: 4, 8, 9, 12. If you factorize them, you will find factors other than 1 and the number itself. If you are picking up 8, then factorize it and you will find many factors other than 1 and the number itself. So these are the composite numbers. Now we know what are the composite numbers and the primes. Let's talk about order and uniquely now. To understand the order, let's have a composite number 156. Dividing it by the prime number 2, we get 78 as a result. Again, the 78 is a composite number and can be further divided. So we will again divide this number by the 2 prime number and that will result in 39, and the process goes on until it results prime at last. Now you can see the order of these prime factors of composite number 156. Can I change the order of this factorization of 156? Suppose if I divide this composite number by 13, I will get 12 as a result. Then again I will divide it with the 3, so it results in 4, and further it can be divided to result in prime numbers. Whether this order or this order, factors are the same, but the order changes. In this, the order is 2 multiply 2 multiply 3 and 13. In this order, 13 multiply 3, 2 and then 2. In this example, factors are occurring in this way, and this example, factors are occurring in this way. Both results in the composite number 156. Hence, the prime factorization of 156 is unique. Unique means whether this way or this way, we are having the same prime numbers on both sides. So this is a standard form because this is coming in the same way. Unique means the standard form, that you are writing those numbers in the same way over time. That means again and again. For example, if you are writing natural numbers and you have been writing these numbers from 1, 2, 3 to infinity, and you have been writing it ever since you knew them. So what is this? The standard form. You know the standard form. That's how we write the natural numbers. So this standard form is unique. For the whole number, the standard form starts from 0, 1, 2 to infinity. So that is the standard form or unique. Hence the prime factorization of 156 is unique except for the order. Because you see, order is keep changing here in this example and in this example, and we can do it in other ways also, as we can divide it by 3 first. We can change it on our own, but the factors, prime factors, will remain the same: 13, 3, 2, 2, except for the order in which the prime occurs. Hence the definition. Now you can clearly understand this. Every composite number like 156, every composite number can be uniquely, that means in standard form, expressed as a product of primes. This is product of primes except for the order in which these prime factors occur. Just like I told you here, this is the same, except for the order. Order in this and in this is different. Based on this arithmetic theorem, let P be a prime number and A is a positive integer. For this, keep in mind the earlier example I have explained that positive integer A in your mind is 156. And prime number, you know very well, after factorizing we got the prime numbers 2, 2, 13 and 3. But just keep these methods in your mind, so you will have clear concept of this process, of this theorem I am going to explain. Then if P divides A square, then P divides A. We have to prove this. Proof: from the fundamental theorem of arithmetic integer, A can be factorized. A can be factorized in what? As the product of primes. A can be factorized as a product of primes. Then after factorization of it, we get, let A, P1 first prime factor, then P2, P3, and the process goes on till we get the last number. So these are the prime factorization of A. But note this: P1, P2, P3 to Pn. These are primes. That's true. But not distinct. Not necessarily so. Not necessarily distinct. Can be same, can be different. Now we know the prime factorization of positive integer A, that was in our mind was 156, was P1, P2, P3, P4 and so on till Pn. If I make a square of this to both sides, what I will have? Which implies, it is telling us that if A square, then it will be equal to P1, P2, P3 to Pn. This is for 1A. What do you mean by A square? Then we have to write prime factors for the other A, because A is 2 times. We have done 1 time factorization here in this. Now for the second A, P1, P2, P3, process goes on to Pn. This is for another A, 1 and 2. That's we got A square. These are the prime factor for the A square, which implies A square is equal to P1 square, P2 square, P3 square, and the process goes on till Pn square. It is given that P is prime. We all know this P is prime and it divides A square. This is given. P divides A square. It is given here. And we have to prove this P divides A. Let's move on and see how. P is prime and divides A square. From the uniqueness of fundamental theorem of arithmetic, it follows that only prime factors of A square are P1, P2, P3 till Pn. Therefore, you will find P anywhere. The P which divides A square is one of any factor, whether P3 or any factor. So P is one of P1, P2, P3, so on to Pn, which implies that P divides P1, P2, P3 till Pn, and straight, which implies P divides A. Or you can simply do it by taking example here. Suppose if I am writing 8, then the factors of it will be 2, 2, 2. Let P be any of it and it divides P1, P2, P3. Any number, pick any numbers. Suppose that P is 2 and it can divide any P1, P2, P3, which implies if this P divides factors which is equal to A, then it can divide A also. The whole process is saying this concept. Hence, it is proved P divides A. Point to be remembered, according to fundamental theorem of arithmetic, 1 is not the prime number. Positive integer P is prime if P is not equal to 1. And why is this so? According to the definition of prime, whole numbers which have only two factors, 1 and the number itself. Any positive integer here. So this is the number itself and this is 1. That is the definition for the prime, and it must be the same for every prime number, like 1 and 2. In case of 2 as a prime number, we'll be having two factors only, the number itself and the 1. But when it comes to 1 and the number itself, both are same, do you find any distinctness in them? They are same and is not following the rule. Rule of what? According to the fundamental theorem of arithmetic, numbers are uniquely expressed. That means they are in their standard form. Standard form. And standard form of prime number is what? That 1 and the number itself will be distinct. And that's what this 1 is not following here. So we say 1 is not a prime number. Let's discuss it furthermore with the statement, with the fundamental theorem of arithmetic, which states that every number can be written as a product of primes in exactly one way. If we write 1 be the prime, then we lose that uniqueness, that standard form. Hence 1 is not a prime.